now. We're seeing some online, and we have a few of our staff and students here at Lower Campus in Suva. I'm Moira. I am the communications officer here at PACESD USP. So I've been tasked to introduce our speaker for this afternoon. I'll be very, very brief. Dr. Arnold van Rooyen is a coastal oceanographer at the University of Western Australia. He's also an engineer currently working as a postdoctoral researcher in the Oceans Graduate School and the University of Western Australia Oceans Institute. His current research aims to provide better estimations of coastal protection provided by marine ecosystems such as coral reefs and salt marshes using large-scale laboratory experiments plus detailed numerical modeling. I'll leave the rest if you'd like to ask him questions. We have a question and answer session after his presentation. I'm also like to welcome the regional participants. Mbula again, bonjour, and Dr. Arnold, over to you.
All right, thank you, Moira, and Bula, everyone. I hope everyone can hear me well. If not, then I'll probably see someone wave at me, I guess. So thanks for joining this this seminar or webinar. You heard already a bit on my background. So I'm in the University of Western Australia in Perth, and today I'll be talking a bit about how we in our research use models to look at coastal protection offered by marine ecosystems. So I probably got you excited with that nice photo on the flyer. There won't be too many of those pretty pictures in this talk. It will be more about the picture that you see in the background now. Hopefully still a bit interesting for you to hear about this stuff. So just a bit about myself, because you probably hear from my accent and my name that I'm not Australian, although I do live here. I've been here for a few years now. So I thought I'd give you a bit of a background of where I'm from. So originally from the Netherlands, which is a very small country in Europe, right next to Germany, Belgium, and UK on the west side. And most of my time I spend in two places. One is called Katwijk and the other one called Delft. And so I grew up in Katwijk, which is a coastal town. You can see some photos of me on the beach. Like most of the kids, I love being on the beach and building sandcastles. So maybe that somehow motivated me to pursue a career in coast engineering. Not sure. And I particularly like the bottom photo on the right, because there's a few interesting things about it. So that's me, my mom, and my younger brother playing with snow on the beach. So this amount of snow on the beach hasn't happened probably in a couple of years now. So it's quite rare. But probably the most interesting thing is if you look at the church and you see that little dune in front of it, it almost seems like the church is at the beach. And in fact, Katwijk was also in the early 2000s defined as one of the weakest links in the whole Dutch coastal protection. And maybe some of you might know that the Netherlands has a long history of fighting against the ocean or keeping the water out. And this was one of the weakest links, as you can see in the photo. If you have a bit of a big storm, that dune is basically gone. And I don't know if there's any football fans, but the place where I'm from is also, we have a local hero called Dirk Kuyt. He played for Liverpool and for the Dutch national team. So that's probably what it's most known for now in the broader public. He still lives there, by the way. That's pretty cool. So then I moved to Delft. So I did my studies there, studied civil engineering, and then started specializing in hydraulic and coastal engineering. And then after I graduated, started working for Deltares, which is a Dutch research institute that has a lot of experience and expertise in coastal engineering and coastal modeling specifically. So modeling of waves, currents, sediment transport, beach erosion, but also long-term morphodynamic changes, like the development of estuaries, those kind of things. And just to go back to my hometown, so in 2005, if you look at the photo with the small dune, I just got a photo from Google Earth where you can see that same church highlighted with the circle. You see that little dune row in front of it. But just before I left for Australia, they did a major construction there. So you can see it in this photo. They built a huge dune, they extended the beach, and they're now very well protected. And they actually have what they call a dike in dune construction. So they basically have a hard structure, and on top of that, the dune to give optimal protection. And they even have a parking garage in there as well. So it's if you're ever in the Netherlands, don't just stick to Amsterdam, but also definitely visit this town, especially if you're interested in coastal engineering. So that's sort of the background. And then in 2015, I moved to UWA, University of Western Australia in Perth. And from then on, I focused a bit more on the fluid mechanics side of things, so more on the detailed hydrodynamics around ecosystems in coastal settings, combination of physical and numerical modeling. So I did my PhD there, finished last year, and now working as a postdoc, really more focusing on coastal protection offered by natural systems. So to start the actual talk, so what I wanted to briefly go through today with you is a little bit of an introduction to coastal hazards and some of the conventional engineering structures, because I think probably many of you are not coastal engineers, maybe more marine scientists or from other disciplines. So just give a bit of a background in this field, and then specifically talking about how marine ecosystems fit in the whole coastal engineering picture. And then I'll show you some examples and a bit of motivation why and how we use physical models and numerical models to help answer a number of research questions. And then hopefully, there should hopefully still be some time for discussion or questions if you would have any. So as coastal engineers, when we talk about coastal hazards, we typically we'll be talking about coastal flooding. So when the water level gets too high due to the combination of tide and wind-driven surge and waves, you might end up that you get flooding, which is often a problem because people might have their house there, or there might be other infrastructure. Another aspect is beach and dune erosion. So if you have a big storm, the dunes and the beaches might erode significantly, which is normally a natural process. But if you have something built close to the shore, or if it's more of a longer-term structural problem, then it can become an issue where coastal engineers are asked to think about how to prevent it. And the photos I showed you are from a very recent storm here in Perth. They named it a 1 in 10 year storm. I think it was the 26th of May. So in the middle picture, you see very big dune erosion. It's about a 3-meter scarp. And on the bottom right, you see the waves. There's basically no beach. There's the waves just running on the beach, and they're hitting the dunes. That's why you get this dune erosion. And the other photos are from other locations. And of course, there's the climate change effect. So sea level rise is, of course, as you probably all aware, is a challenge. How we're going to deal with that, and how we're going to make sure that we stay safe. And also the change in storm intensities, for example. So there's a lot of discussion. Sea level rise is, of course, quite well defined, and although there's still a lot of different estimates, but our scientists, I guess, agree that sea level rise is happening and it's going to happen. But with storm intensities, it's a bit of a question, like what's going to happen to actual storms. And the latest research suggests that there might be less storms in general around the world, but they might be more intense. So that's something we need to think about as coastal engineers as well. And then sort of the traditional coastal engineering protections, I just put a few photos here, but you're probably well aware, is that we put hard structures there, seawalls, breakwaters, try to keep the beach, try to limit the wave impact on the coast. But yeah, there's a few drawbacks of these. And so at the same time, if you look around the world, there's many shorelines that are actually fronted by marine ecosystems. So just as an example, there's many places, I'm sure in Fiji as well, with corals, or mangroves or seagrass. And at the same time, we don't really know how these ecosystems affect waves, for example. That we don't really, we do know that a little bit now, but not as well as we would know the coastal processes on a coast that doesn't have any of these systems. And at the same time, these systems are also disappearing in many places around the world. So there's definitely a motive to try to understand what these systems actually do in terms of coastal protection before, at some locations, they might just disappear. And at other locations, it might be worth restoring because instead of building maybe a seawall, you could restore a mangrove forest. So the idea of a nature-based coastal protection in the most sort of general sense is shown in this picture, where you would maybe already have a dike because people build their houses in risky areas, and you might have a tidal marsh in front that will have an effect on the waves, so that the impact on the dike is relatively small, and that's how everyone stays safe. But then if the tidal marsh would be to disappear, it might be that the waves will just freely propagate towards the dike, might damage the dike, and even cause overtopping. Another way to show this in this video, I'm not sure if actually videos work very well via this system, but hopefully it does. But what you basically see here is someone made a very simplified flume experiment. They put Duplo dolls on the beach and generated some waves where on one side there's some sort of vegetation, I think it's watercress, and the other side there's not, just to kind of show you the idea. So around the world, there's been a lot of initiatives to look more into this, and there's been a lot of funding going into quantifying how much protection these systems actually give, and how you can actually integrate it in engineering solutions. So there's just a few names here that there's, especially in Europe and in the US, there's a lot of focus from governments on trying to, as they call, work with nature or building with nature, engineering with nature, but essentially using the natural processes in your benefit, and not try to work against them. And so it's kind of a hot topic, but there's a lot of challenges involved, I would say. So like I said, traditionally it's kind of neglected that you would have something in the offshore, so you would not really think about it when you think about coastal protection. So it's kind of a new field, which is shown in the left plot. That's the number of publications per year that you can find online specifically on this topic. So you see that only since like 2005, 2006, it really started picking up, and people started really looking into how vegetation affects waves, for example. There's a lot of questions around restoration and protection, because if you restore an area that there's a very strong connection with the wave conditions, for example, because if you try to restore something but then there comes a big wave and destroys it again, then there's no point. And so there's definitely a lot of challenges there. One of the things with adaptation to climate change and sea level rise, so some of these species will be able to maybe grow with climate change. So if you have a seawall, of course, if there's sea level rise, the seawall won't go up, so you need to do a big investment again. But there's more and more studies showing that, for example, mangroves might be able in some locations to capture more sediments and grow vertically with sea level rise. So like an adapted coastal protection. And then on the right is kind of to show you how complex it is. So traditionally, we would just look at the first sort of loop. So hydrodynamics, waves, currents, and then that gives sediment transport, and then the coastline changes. There's erosion or sedimentation, and that feeds back into the hydrodynamics again. But if you include seagrass or corals, actually not sure if I can. You can probably see it now better. So in this particular example, seagrass and corals, there's interaction with all these different components. So it makes the picture quite complex. So then a bit about physical modeling. What we do quite a bit here at UWA is using wave flumes, and then put some sort of ecosystem or some representation of an ecosystem in this wave flume, and then study how it interacts with the waves. And that is the main reason why we do that in the lab. Is it gives us a lot of freedom to select particular wave conditions, for example. So it's not if you go out in the field and you need to kind of hope for the right wave condition or the right storm to pass by. You can simulate anything. And also the ecosystems themselves. You can imagine a seagrass meadow might be very spatially non-uniform, which is very difficult to then try to understand how it actually affects waves. So we try to simplify it with uniform vegetation fields, particularly with seagrass, because it's flexible. That increases a lot of that increases the complexity as well. So we sometimes represent it by rigid cylinders. And the other thing is, like, you can really look into specific processes and isolate them. So you can, like in a coastal setting, there might be waves, there might be currents, there might be wind. Whereas in the flume, we can say we just want to have waves, no currents, no wind, and just look at the effect on the waves, and then try to understand that, and then slowly build up the whole picture of what's actually happening. And of course, there's also risks included with field collection. If you go into a coral reef during a cyclone, then well, I bet the university probably won't allow you to do that. Whereas in the lab, you could probably simulate that to some extent. So this is just an example of some of the work that a colleague of mine did in her PhD. And she looked at wave propagation over seagrass mimics, and she was particularly interested in the effect of flexibility of the vegetation. So you see on the right plot, she compared rigid mimics of some sort of vegetation with the flexible ones, which look a lot more like seagrass. And she actually found that the processes are quite similar. Of course, there's the added complexity, but the velocities that she was measuring and the effect of the vegetation on the velocities were the effect was quite similar. And this is from a recent experiment that I worked on a couple of months ago, where we further simplified vegetation. So in this case, it's just rigid dowels, and we particularly want to look at the wave run-up level. So many of these studies have looked at wave dissipation. So you basically put something in your flume, you look at the wave height before the vegetation, and then after the waves have passed the vegetation, and it gives you an idea of how much energy they absorb. But no one has really looked much at what that means for the wave run-up. So actually on the beach, the waves washing up and down the beach, which is directly relevant from a coastal protection point of view. So in this case, we represented by rigid dowels as a first step, because this is kind of the initial phase of the project. And later on, I'll show you some slides later. We're going to do some more complex stuff, and then we try to measure so the other measurement locations are wave heights that we measure across the flume, and then with a camera we try to estimate the wave run-up levels. This is how that works. So you face the camera to the area, and then these yellow squares or yellow crosses are some control points. So there are points that we know the locations and the heights. And then we need to correct the photo for the perspective that the camera had. And then with some edge detection techniques, we can track the wave run-up level going up and down the beach. So if you do this for every frame within the video, so it's 128 hertz, so let's give 128 photos per second, you can really see the waves running up and down the beach, and then detect the pixels that are in the leading edge of the swash, and that gives you an idea of the run-up. And then this is for the bare bed case, but you can do the same then for the cases with canopy. So this is very much ongoing work, I would say. But I do have some very preliminary results of this, where we actually found that the wave heights didn't change too much with different densities of the canopy, whereas the run-up levels did change a lot, which in itself is quite interesting, that the waves, even quite high up in the profile, are very similar for different densities of vegetation, but actually run-up level differs. So the denser it gets, basically the less far the water gets, which kind of makes sense as well. So that's just a little bit about physical modeling. So now I'll talk a little bit about numerical modeling, and I just use this. I got this slide once from somewhere else. That was always a good introduction for people that have no experience or have no idea about these kind of models. So essentially, what I always like to compare it with is that like a numerical model is essentially what they also use for weather predictions. So they run some scenarios based on the data they have, and they predict the weather for tomorrow. And that's essentially what we do with a model in a coastal engineering as well. So you can use them to predict things. You can use them to help design. You can use them as a communication tool, as a sort of a laboratory. So you can test different things and see what happens. There's always a bit of the question, like how real is it? Some models are more detailed and more accurate than others. And And yeah, and definitely it's the use of models is also a bit of an aspect to think about, because there's a famous garbage in, garbage out paradigm among modelers, where you say, well, if you have a perfect model, but you put garbage data in, then you have garbage results. And you can also have perfect data, but if your model is garbage, then you also have garbage results. So you need to have perfect data and a perfect model, and then you can sort of trust the results. And I'll show you some examples of how we use that. So one of the projects I worked on last year was together with some biologists here at the university, and they were very interested in trying to understand why specific species grow in specific areas. So you can sort of see that in panel C in the left column. So every symbol is a different species. So species of seagrass in this case. So the white triangle is one particular species, and the black circle is another species. And they had done some analysis and they had some suspicions why that might be, but they didn't really measure any hydrodynamics or waves. So they only measured. They mainly measured, or they collected data on density of seagrass and what species it was. So then we got together and kind of talked about how we could try to solve that. So we ended up running a coastal engineering model, or a coastal hydrodynamics model, DELF3D, coupled with a wave model, SWAN. And we actually found a really clear relation between the wave heights that are found in areas with specific species, and that turned out to be matched with results from other studies on the roots, for example. So the seagrass that was more offshore and was subject to higher waves had a much stronger root system, so they could withstand bigger waves. And we did that with running a few storm scenarios. But it's typically something, that where a numerical model comes in quite handy, because it can help you understand why things are the way they are. So in the following, I'll talk a little bit about XSpeech, because it's a model I've been working on myself quite a bit, and also Lenzi Muna from USP, or used to be at USP, used it in his studies, and particularly looking at how you can have vegetation in this model. So XSpeech originally is a model for storm impact. So it's designed to calculate dune erosion, to calculate beach erosion, and also the hydrodynamics that go with it. It's quite we would say, sort of detailed model for coastal engineering perspective. So we typically run it for kilometer to a meter scale. And it's been out there now for over 10 years, and it's been widely used. There's hundreds of publications that have used the model online. And also coastal engineers and managers use it. And a couple of years ago, we got a request from a client to be able to include mangroves in XSpeech, because they wanted to look at wave attenuation by mangroves. So we got a little project where we worked on getting vegetation effects into XSpeech, and we wanted to keep it generic, because we wanted to not just do mangroves, but be able to do seagrass or salt marsh or other types of vegetation as well. And essentially we worked on getting the effect of vegetation on wind or swell waves, but also infragravity waves and currents, and also the effect on the mean water levels, the effect on wave setup. And I'll show you some of that in the next slide. And we wanted to make sure that the model was able to include vegetation that varies vertically. So typically a mangrove tree with a root system, a trunk, and a canopy, that we could somehow schematize that, and also that we could have multiple types across the model. So you could have multiple species, or you could have different densities at different locations. So you wouldn't have just one particular vegetation type. And we also made sure we included these effects in all three modes of XSpeech. So XSpeech runs in three modes that all have different levels of accuracy, and also levels of computational power, so how long it takes to run the model, basically. So those are these three models. So essentially, you can run the model in kind of a large-scale mode, which is similar to DELF3D, where the wave conditions are constant in time. They might vary on the hour scale, but They wouldn't vary on like a minute or second scale. And then there's the hydrostatic, the middle one, which is the standard version of XBeach, which solves these infragravity waves, so these longer period waves that are important for dune erosion. It solves it directly, and then it solves the short waves on the wave group scale. So there's these big blue blobs are basically wave groups that are propagating towards the coast. And on the bottom one, you see actually the individual waves. So the non-hydrostatic mode solves the individual short waves. So just to give you an idea of the level of detail, because basically these three simulations are doing the same thing. It's just that if you go from top down, your computational time will increase a lot, but you solve more processes, so you can look at more detailed effects. If you go up, then it's the other way around. So your model gets a lot faster, but you lose a lot of information. So then just a tiny bit of theory on this, on how to include this in XBeach. So the kind of the accepted theory on wave attenuation by vegetation is that it's related to the drag. So the drag force that the vegetation exerts on the waves or on the water column, and that the dissipation is basically equal to the work done. So the work is equal to the force, so drag force times the velocity. And the key thing is this drag force which you need to calculate. And at the moment, sort of the state-of-the-art method to do that is based on single cylinder theory. So that comes from offshore engineering theory from the 50s, where you have the so-called Morrison equation that includes for waves. Then there's not only the drag force but also the inertia force, and that has some parameters. And basically the main sort of input is that originally it's designed for a rigid cylinder, so now we just multiply it with the number of cylinders per square meter essentially to get an idea of what a vegetation field would do. And if you look at the parameters that we basically include, is so you need to have some sort of density, so units per square meter of stems. So that could be the number of blades of seagrass per square meter, for example. You need to have some sort of diameter or blade width, which is called it's really hard to collect, I know, probably to get a good representative value, but most of the uncertainty in this model actually is in the drag coefficient and the reference velocity, because drag coefficient, we know it should be around 1 for cylinders, but of course seagrass is not a cylinder, and also mangroves are not cylinders, so there's a lot of work being done on trying to derive drag coefficients for more realistic ecosystems. And then the reference velocity is another aspect that hasn't been looked at much, but it basically comes down to the combination of drag coefficient and reference velocity needs to match, because the velocity inside a seagrass meadow might be very different than the velocity above the seagrass meadow, and often people don't really account for that. And then they sort of tune their model and get a good value for CD, but then it might vary a lot for which reference velocity you basically picked. So there's definitely some key challenges. So how do you get representative values for ecosystems? You need to somehow estimate them. There's also very complex morphologies like corals that don't really fit this single cylinder methods directly. And then, like I said, the drag coefficient depends on the velocity, but it also depends. But the velocity also depends on the drag coefficient itself. So it's a bit of a complicated story. But anyway, we included that sort of the state-of-the-art theory in XBeach, and on the left you can see that animation that if you have some sort of vegetation, then you see the waves are being dissipated, so represented by the blue, dark blue envelopes. So here's some validation with lab experiments. So on the right you see the wave heights across the beach slope, which is shown in the bottom with the location of the vegetation. So you see the measurements are represented with the markers. So without vegetation, that's what the measurements show and what the model shows, and then with vegetation you get this dissipation. One key aspect that hadn't been looked at much is the effect on wave setup. So when you have waves propagating towards the beach, especially if they're quite big, they also increase the mean water level, which we call wave setup. And typically that effect's kind of ignored. But you see in the data these squares, there's basically no There's basically no increase in water level, and our original model was the blue one that didn't predict that. But then with the implementation we did, we could account for that. So it's basically another important effect, because if your mean water level is also lower, that's sort of a double effect, because that will also make sure that the waves run-up will be less and that the waves are dissipated more. So we've done a little bit of work on this drag coefficient. I had a master student a couple of years ago who collected data in the Mediterranean, in Spain, across the seagrass meadow, and try to come up with the relation for the drag coefficient. You can see there's quite a bit of scatter in this relation, and yeah, she found that the so-called Culligan-Carpenter number, which is a function of the wave velocity, the wave period, and the blade width of the seagrass, gives a reasonable, you can get a reasonable formula that gives you the drag coefficient that you can put in the model. But that's that's sort of the problem with the drag coefficient, is that it includes a lot of uncertainty that we don't know. So it includes flexibility, it includes also that the flow velocity inside the canopy can be very different than above. It includes spatially non-uniformity. So more recently here at DWA, we wanted to look specifically at the effect of the velocity inside the canopy. So if you look on the right plot, that's a measured velocity, wave velocity profile. So it's the black dots where the dashed line is the top of the canopy. You can see that the velocity inside the canopy is a lot smaller than above. It's less than 50%, which is what you would expect, because wave propagate over this dense canopy, then there will be some attenuation of the flow. But this typically isn't accounted for other than tuning with the drag coefficient. So we actually worked on adding as we call a subgrid model. So that's the you see on the left. I won't go into detail in the equations, but in the original implementation, we basically just had a drag or a vegetation force that had drag and inertia, which is the red F, which is then calculated based on this Morrison equation. But then the question was, what do you use as this velocity? Because typically you would then use the velocity that's above the canopy, because that's what the model gives you. But if you look at the plot, the velocity inside the canopy is actually very different. So we implemented a subgrid model that then calculates this in canopy velocity, and then with that calculates the drag force, and the drag force and inertia force. And what that does is it reduces the uncertainty, because although we don't account for flexibility and all these kind of things yet, we do account now for this canopy flow attenuation. And if you look at the results, you can basically, if you compare the model results with laboratory data where we actually use rigid cylinders, so to simplify the whole problem and not worry about flexible stuff, you can see that without calibration you get a really good match. So the colorful lines are all variations of this implementation, and the black line is the original one. So if you wouldn't calibrate your model, you would really overestimate the effect of the canopy in this case. Whereas if you do account for it, and there's in this particular case, I looked at the different combinations of velocity, specific velocity, and or reference velocity, and the drag coefficient. But in general, they are pretty similar. Then you do get a very accurate result. So this is just for the drag coefficient that's uncalibrated. Like I didn't tune it or anything. So that's, yeah, gives some confidence that if we include that effect, then at least we have part of the puzzle that we solve. And then I got some questions. Oh, but why don't you then just use a two-layer model? Because the whole point of this XSpeed implementation is that it's a subgrid model, so it doesn't. So there's interaction between the two at each time step, but it's not directly solves both equations. And the reason for that is that XSpeed in itself is depth average, so it only calculates the depth average velocity. And the reason why we kept it like that has to do with runtime. So we basically get very similar results with a model that does do actual two-layer simulations. It's a model called SWASH from TU Delft, but it's 3 times slower. So for large areas, if you want to model large areas, factor 3 in runtime is can be quite significant. Can mean that instead of 2 days, it takes a week to run your model. So yeah, and then and if the results that you're looking at are still good enough, then that's sort of the motivation behind this subgrid model. So now I'll just show you some examples. Just double check the time. Yeah. So here's just some examples for this X-Beach model with vegetation. So the first one is in Albany, which is a small town in Western Australia. So you can see on the right, there's this nice bay called Middleton Bay. And one of the issues there is they've been having a lot of erosion on the east side of the bay, or actually northeast, I guess. And if you can see it on the screen there, but there's like a seawall that they constructed because there's a little town here, and it was just kept on eroding. And they've had a lot of seagrass loss in the 80s. And they're still a very healthy sort of patch in this orange circle, but there used to be seagrass all around. So they're kind of wondering, how does does the seagrass actually is the loss of seagrass the cause for this erosion, or is it something else? So we had a group of undergrad students from UWA that did a field campaign there. So they went out and they took some surveys and they defined 3 areas with different densities. So the area number 1 is a very dense area, the healthy area I just showed you. Area 2 is sort of it's not super healthy, but it's also not too bad. There's still quite a bit of seagrass. And 3 is where the seagrass is really degraded compared to the situation in the 80s. So they took samples of the seagrass. They tried to estimate the density and length and these kind of things. And then they also put instruments there to measure the wave heights. So that what you see on the plot on the right, those are locations where they put instruments to measure wave heights. So in particular across this dense patch, we put a few instruments. And then, so with the model, basically we set up the model for this area that you see on the right as well. And then, looked at how the model basically predicted the wave generation by the seagrass, or if you could get a good match, which is shown on the plot here with the 2 colored lines. So blue is measured and orange is from X-Beach. And then the dashed line is as if there was no seagrass. Because there's always a bit of discussion especially among coastal engineers that say, well, seagrass, it's so flexible, it's often deep and it doesn't really do anything. But what we saw here is that there's definitely a small effect. Even the waves are quite small, but they're still, it's definitely an effect worth noting, and especially on longer term, it might have an effect on the beach, the situation of the stability of the beach, basically. Because if you have over longer term waves that are just 10% smaller, but it happens over a decade, that might in itself provide some more stability of the beach. And then kind of the fun thing with these models I find is that if you have a bit of confidence that the model can somehow represent or simulate these processes, then you can do some what if scenarios. So I was really interested in the beach erosion problem, but we didn't have time and didn't have opportunity to actually measure any beach related data. So I just turned on the model, turned on the sediment transport, and then looked at how the different seagrass meadows affected beach erosion for a typical storm. So you see in this plot on the right for it's a storm of 3 hours. In the current situation, that's the blue line, and then if you would have dense meadows everywhere, we would get the red line, so a little bit less erosion, but not too much. But then if there's no meadows at all, the model would predict that there's a lot more erosion. So that's kind of to show you how you can use these models. Of course, there's no data to compare it to, so you have to be careful with interpreting these results. So this is another example of X-Beach that we used with vegetation, in this case with kelp. So this is about a case in Turner's Beach in Tasmania, where there's a beach that suffers from erosion during storms. And they're also fronted by the giant kelp forest. So these are, like the name suggests, they're really big kelp species, can grow up to 30 meters deep, and they reach all the way to the water surface. And the thing with kelp is that there's also a lot of discussion about how it actually would potentially help with coastal protection, because it's also so flexible that a lot of people would think, well, it just moves with the waves and it doesn't really do anything. But on the other hand, it is also often quite buoyant. So the buoyancy of the kelp might actually increase the drag of the vegetation on the waves. So there's some, well, there's definitely more studies needed, but there's some suggestions that it might actually be an important effect. And also it's really tall, like 30 meters tall, so it affects the whole water column. So this is sort of a nice case study where there was some data available. There was not really any hydrodynamic data or sediment data. So we did some validation with a lab data set that was done for or using kelp or artificial kelp essentially. And then when we saw the waves were well represented by the model, and also the dune erosion that was found in the lab experiments was reasonably well predicted by XBeach. And then we just got the field data that was available, so beach profiles, kelp characteristics, typical storm conditions, and just run a number of what-if scenarios. So kind of looking at, so what if the density changes of the kelp? What if maybe due to climate change or other reasons there's no kelp anymore? What's going to happen? And what's going to happen for different storms? And what's going to happen with different sea level rise scenarios? This is just a conference paper that we did last year. But it kind of gives you an idea of what these models can do. And of course, the key thing is that we need more data. Like, people need to go measure these things to give more confidence that these models can actually do something with a certain level of certainty. But yeah, I kind of like to think about these models also to motivate people to kind of think about, these models are process-based, so there's not really a direct reason why you wouldn't trust them. Of course, you have to be cautious. But yeah, they're definitely helpful tools, and to try to understand different complex problems that you wouldn't be able to understand just by looking at a Google Earth picture, for example. So this is just one of the last slides. This is not so much work that I'm involved in myself, but there's a few people in our group that do really detailed numerical modeling. So they really talk about millimeter to centimeter scales. Which in itself I think is really interesting, because although these models take forever to run and they need to be run on a super fast computer, they do solve processes on such a detailed scale that calibration is often not needed or very limited. So the animation on the right is actually represents kelp, although it doesn't look like it much, I guess. But the idea is that if you have a buoyant type of vegetation that sticks upright and moves with the waves, and that you can change the buoyancy and then look at the effect on the waves. In this particular model, the model becomes a very powerful tool, because you can basically play with all these parameters without having to have expensive equipment or having to book lab time or spend a lot of time trying to work out what materials to use. So we have a PhD student now that just started with this, but has already done a lot of testing with his model, and then uses that to design his experiments. And then later on, he'll probably have a bit of a combination of both, where you can look at specific data from the experiment in a better way, whereas other processes are easier to get out of a model like this. And then there's some other type of models that really capture the flow through canopies. This is a top view. So on the left is a top view of a vegetation field, I would say, and the colors are the velocities. Or the maximum velocity, so there's the velocities going through the canopy that the model calculates, and this is also without any calibration. So this is just with cylinders, but you could easily put more complex shapes also in these models, and then get information on the velocities on a very detailed scale. So as a bit of outlook, so some of the ongoing work at the UWA, I kind of showed you quite a lot of simplified sort of models, so based on this rigid cylinder theory, which is still, I would say, state of the art at the moment. But there's a lot of groups around the world trying to include more realistic or more accurate approaches. So within the project that I'm also working on, we definitely want to kind of make the step from what you see in photo A on the bottom left, and then look at flexible ones. We've done a little bit, but we don't want to do it more. We also have people 3D printing corals, coral colonies, and putting them in the flume. And also people looking at mangroves, so really at the root structure and trying to understand how that affects the different processes. I think the end goal is, so we'll be doing a lot of physical modeling with these systems, and focusing definitely also on the wave run-up, because it hasn't been done much. But But then the idea is that hopefully we can come up with better formulations that we can include in models like XSpeech, so that if you put a seagrass in there, that's you basically reduce a bit of the uncertainty that we get with this drag coefficient method, which is often, there's so much complexity put in just one coefficient that makes it very makes it a bit tricky, because you can sort of tune your results to make it look good, but then it also loses its predictive capacity, because you can always get a value from literature and say, well, this is a value that's probably somewhat good for seagrass, but then it's a bit hard to say, well, how does it actually work then on a different location and with different wave conditions and outside the variation that it's been derived for. So this is all very much ongoing work. We just started this project. So I think, this is the end of my talk. I hope I'm still in the time. So I'd like to thank University of South Pacific for giving me this opportunity, and then specifically Dr. Anesh Singh and Dr. Gillian Brody. So if you'd like to contact me, I put my contact details there. Also, in case there's any students that are interested in this kind of research, definitely go have a chat with Anesh or Gillian and see if there's any projects, or if there's any way to maybe collaborate with people here, with me, or with other people here at UWA, if it will be of interest. But thanks for your attention. I'm happy to take any questions, of course, if there's still time. Should be, right? Yeah.
Thanks, Harold. Anyone here or online has any questions?
Yes, I have a question.
Go ahead, Christophe.
Yes, thanks, Anesh. So I'm Christophe Menkes from IRD in New Caledonia. Thanks for this very interesting talk. That's of quite interest to us here, actually. I was wondering, coming back to your slide on the Albanese beach, where you had, the next one, I guess. The time, so I understand. So the model is actually really good in fitting the observed wave height, right? HM is the wave height observed. This was not fitted. This was not. This came as the fact from the implementation of the subgrid model, and just came as that.
No. So this one is calibrated. Yeah. So this was actually done before we did the subgrid model. But I think in general, if you would use the subgrid model in this case, I would still not expect that it would be give a good match right away, because of mainly because of the flexibility of seagrass. So I think, with the subgrid model, we try to sort of eliminate one uncertainty, which is this canopy flow attenuation effect. But then there's still other uncertainties and other complexities like flexibility or the spatial non-uniformity of vegetation. So I would expect that for this case, we would still, for example, have a smaller drag coefficient than 1, because we need to account for the flexibility of the seagrass.
Okay. All right. And this X beach it works on a non-regular grid. It works on the adaptative grid, or is it?
No, it just has regular. You can do curvilinear grids.
Okay.
So you can have spatially non-uniform grids and curvilinear. They are so at Del Towers, where the developers of XSpeech are. They have included XSpeech functionalities in Del3D Flexible Mesh, which is a new software package that does use unstructured grids. So there's some functionality that you can use in Del3D FM if you would have that. but I'm sure, and I don't think the vegetation part they've moved there already. Because I used to work at Delta actually until February this year, but the latest I heard is that they were I think it's just like the waves, the infragravity waves, and the wave groups that they've included in Delta 3D FM.
All right. Okay. And last question. Sorry for
That's
the
okay.
time I'm taking. The next slide, I think, is the one I'm. No, so it's the next after this one, with the return period. The one with the return period with storms. Why is it that for the 100th years, the last panel, why is it that the second panel seems to have a really different behavior than the? I mean, I'm not sure I understand how we go from the first panel to the third panel. So it's the storm intensity that is changed in these experiments, right? No.
Yeah.
And so what?
Yeah. So it's all relative. I remember I had to do this bit of in a rush and try to get it on a bit of a good plot. But so it's all, so you can't really compare, I guess, the three directly. So of course, a 1-in-1 storm has a lot less impact than a 1-in-100-year storm. So so all these plots are related to having no kelp, basically. So right. So that's why they all start at 1, but it's of course not the same. They're not the same absolute erosion values. And sort of the key sort of result we got from this is that we didn't expect them before, and is that the sea level rise effect is not really that clear. So there's a bit of a mixed effect in if you have a higher sea level rise scenario, whereas the kelp density does there's sort of a clear trend going from no kelp to 10 plants per square meter to 25 plants per square meter. You definitely get a decrease in erosion. But between the sea level rise scenarios, it's not like it differs per scenario, per simulation. Because sometimes the like even in, for example, the top plot in a 1-in-1-year storm, the densest kelp, it shows that the sea level rise with 0 has most erosion, basically.
Yes.
Which is a bit counterintuitive, because you would expect if the water level is 80 centimeters higher, then I would expect there to be more erosion there.
Yes. Okay. Well, thanks a lot. Thanks for your very good talk, and thanks for Onesh for inviting me on this remote meeting. Thank you.
Thank you.
Thanks, Christophe. Any other questions? If not, then thank you very much, Arnold, for availing yourself for this presentation.
No worries, my pleasure.
Yeah, this seminar was recorded, and it will be uploaded on our seminar website probably tomorrow. So thank you all for joining. Have a great week and weekend.
Thank you.
Sorry. Thanks, Arnold. It's a pleasure having you.
Talk to you later.
All right. See you. Bye.
Bye.